solve compound and continuous interest problems. So before we take a look at what that means, let's go ahead and look at our warm-up. It says in a linear function, y equals 2x plus 3. So we reminded in a linear function, the slope or the rate of change is 2, and we always see that in front of the x. We always know where to find that. And the y-intercept is 3. So we always know where to find that plus or minus. So last year we learned about exponential functions. So the question is what does the 3 and 2 represent in the exponential function? So when we look at exponential functions, we don't have a slope because it's not a line. So we call it a rate of change. And that rate of change always has an exponent of x. So in this case, 2 is our rate of change. This would be doubling as we continue in our pattern. So we would be multiplying by 2 to get each consecutive term, which means in front of that rate of change is always the y-intercept. So in this case, 3. So if we were going to graph this, we would be able to start at that intercept point. So today we're actually going to be working with exponential functions in a little bit different manner, but that just warm-up just kind of got us thinking about those exponential functions. So let's go ahead and keep working with our notes. It says the standard form of an exponential function is, so we remember this from last year. I'm going to use our function notation. F of x is equal to, so a, which would be that intercept spot, times b, that rate of change to the x. And specifically, a couple of things to keep in mind. A cannot be equal to 0. And if we think about that, if a was 0, 0 times any rate would just be 0. So we don't want it to be 0. We also want our b value to be greater than 0 today. And we don't want it to be equal to 1 because anything to the first power is just, or 1, to any powers just stays 1. So for these problems that we're doing today, those b values need to be greater than 0, but they can't be equal to 1. So we're going to start off today by using what's called the simple interest formula. So this simple interest formula states that capital A, which we'll talk about what that is in a second, is equal to capital P times the quantity 1 plus r to the t power. So this is an exponential function. It's got all the same properties as our standard form does. We've just got a few things that are added. So let's go through what each of these pieces mean. So capital A is what we're going to refer to as our final amount. So we're going to be solving problems today, a lot of times dealing with money. So in this case, A would be our final amount. Capital P in the business world stands for principal. Now, principal, another way to maybe say this is that this is the original amount. How much did we originally start with in the problem, the principal? R is going to be our interest rate. So everything we do today is going to have some kind of an interest rate. And we're going to, as it says right below this note, we're going to be expressing interest rates in decimals. So a rate is usually given to us as a percent, but we know that we can't operate with percent, so we're going to change those to decimals. And T, as we already have used in so many other functions, this just represents time, and specifically, we're going to be working in years. So let's look at this first example. Austin deposits $450 into a savings account with a 2.5% interest rate. How much money will be in the account after 5 years? So this is the type of problem we want to be able to solve. If he's putting so much money into a savings account and it has a certain interest rate, how much is he going to have after 5 years? So one thing just to start off with, my interest rate is in percent, and we know that we have to change that to a decimal, and we move the decimal 2 places to the left. So we're really going to be working with 0.025 as we plug this in. So this is called a simple interest problem. We're looking for that final amount. We're looking for A. How much is he going to have after 5 years? However, we do have an original amount called the principal. He's putting $450 into a savings account. And in parentheses here, our quantity Our interest rate, he would like to increase his interest rate or his amount of money by 0.025. So we saw this idea of increasing and decreasing a little bit last year. So we have 1 plus as we want to increase by 0.025. And we want to do this for a total of 5 years. So our exponent for t is going to be 5. So we're going to be using our calculator to help us calculate. And you can pretty much just type this whole thing right into your calculator. So I'm going to go ahead and type 450. And I'll go ahead and put parentheses. And I know that 1 plus 0.025 is just 1.025. So that's how I'm going to enter that one into my calculator. But it's to the 5th. So we're going to probably get pretty big decimals, and that's pretty normal. But when we're dealing with money, we usually do 2 decimal places. So I'm going to go ahead and think of this as $509. And let's see, 13 cents, because that second 3 isn't big enough to round up. So Austin, if he puts $450 into a savings account for 5 years with 2.5% interest, he's going to come out with $509.13. So at this point, I guess Austin would have to decide, is this a really good thing? Can he get a better interest rate somewhere else for this same period of time? So he's going to make about $59 in those 5 years, which isn't a lot of money, but maybe that's the best that he could do. So let's talk about another kind of interest, and it's called compound interest. So compound interest is a little bit different version of our simple interest. And so we have a formula now that says capital A, so is equal to capital P. But this time in our parenthesis, we have 1 plus R divided by N, and that is all to the exponent of N times T. So as we look to the right of this, it says now the interest is compounded or applied more than once. So now we're not saying it's just every year. We now have another time frame that we could be working with. So as far as what everything means, A is still referring to that final amount, so that's not changing. P is still referring to that principal. How much are we originally going to be putting into this? How much are we starting with? R is still going to be our interest rate, and we're going to still be taking percents and changing them to decimals so we can use them. Time is still going to be in years. We're just going to have to alter our formula to tell us how many times we're breaking up that year. So N, this is our difference here. This is going to be the number of times we're going to compound, which means we're going to have it happen per year. So we're still thinking in terms of years, but how many times is it going to happen in a year? So that's why our equation up here, our compound interest formula, has that R has to be divided by a certain number of times a year. Are we going to do it twice a year, 3 times a year, 4 times a year? But then we need to offset that exponent, because remember, to keep an equation balanced, if we've got something inside of our parentheses, we also should have something with an exponent. So this is essentially the same formula as our simple interest, but because we're dividing that rate a different number of times a month or a year, we also have to affect our exponent. So let's look at an example where we use this compound interest. So it says Cindy and Derek just got married, and they decided to invest $1,000, so there's that initial amount, of their wedding money into a dream CD. And it says a CD is a certified account that pays a fixed interest rate for a specified length of time. So it's kind of just another version of a savings account. Sydney and Derek choose to do a 3-year CD, and it's going to give them 0.0966 interest rate, but they're going to compound it monthly. Now, remember, this is computed in years, so when it says monthly, we should be thinking that there's 12 months in a year. So every month, we're going to add this interest in. So how much money will they have in 3 years? So let's plug this into our formula. We're looking for that final amount. How much money are they going to have after 3 years? But as it says, the principal they're starting with is $1,000. So in our parentheses, we're going to increase that $1,000 by a certain rate, but that rate happens every month. So, and for our case, our rate was a really small amount here, but we still have to move that decimal. So 0.00 as we move that 2 places to the left every 12 months to the, and again, our time is n times t. So we're doing this for 12 months and we're going to do this for 3 years total. So a total of 36 months. So let's go ahead and put this into our calculator and figure out in 36 months, 3 years, how much money we have. So I'm going to type this in exactly how I see it. I've got $1,000, and then in my parentheses, I don't really know what this decimal is, and you could figure that out and add it to 1, but I'm going to go ahead and type it in just as I've got it written on my paper. I'm going to increase this by, and I'm going to put in my fraction, 0.00896 divided by 12 to the, and I'm going to go ahead and just call it 36 because I know 12 times 3 is 36. So again, we're probably going to get decimals on most of these answers, and we're looking for money. So I'm thinking I'm going to round to that 2 decimal places. So 23 cents, because that 4 is not big enough to round up. So in 3 years, if they choose to do this, they would end up with $1,027.23 in this CD. So again, Cindy and Derek need to ask themselves a question, is this good? 3 years and they've only made $27.23. So for most of us, that doesn't feel like that's going to be a lot of money. So you'd have to make a decision. Is there a better option if you're trying to make money, or are you just going to let it sit there and keep making interest maybe for longer? So we've got simple interest, we've got compound interest, and now we have what's called continuous interest. So continuous interest, again, has a slightly different formula. Continuous interest is capital A, which is still going to stand for that final amount, but now we have capital P times E to the RT. And when we use this formula, it's because we're assessing continuously. So now I don't have interest that's just accrued every month or every year. It's continually accruing, which is a little bit of an interesting idea. We also notice in this formula, we have a new letter E. And E is actually a number kind of like pi that has a value to it. And it's an irrational number because it never repeats and it never ends. So right below there, I've got that E is an irrational number, and it's represented by 2.718281828 forever. This continues on in numbers here. And just really quick, since we've seen a little bit of limits this year, here is the limit that represents the value of E. So if we calculate E as it goes on to infinity, as that n value goes on to infinity, we approach this value. 2.71 is usually how it's abbreviated, kind of like pi is abbreviated 3.14. So we're not going to go into too much depth of where this number exactly comes from other than that, but we're just going to use it to calculate. Now, this is on our calculator, so why don't you take a second and make sure that you can find your E. It's on the left side of your calculator near the bottom, 2 up from your on button. To access it, we're going to have to do a second because it's there in blue. So we'll have to do second and this LN button. And you'll learn what that LN button is when you take secondary 3. So let's go ahead and turn to the back side of our notes and let's look at a problem, example 3, that uses this formula. So it says Eva invested $750 into a savings account with an interest rate of 1.2%, and it says it's compounded continuously. So that tells me I need to use this formula. How much money will be in the account after 7 years? So again, we're going to start with our capital A. That final amount is what we're looking for. Initially, she's putting in $750. And we're going to say times e to the RT exponent. Our rate, again, we want to move 2 places so that we have that as a decimal. So I'm going to put to the 0.012 times t, which in this case is 7 years. So I'm going to put this into my calculator and figure out the final amount that she's going to have after 7 years. So we're going to start with 750 times E. So I'm going to go ahead and push that second LN button to get that E. And notice it already is telling me there needs to be an exponent. So for us, we're going to do 0.012, and then we need to multiply that by 7. So in this case, if she leaves this in for 7 years, she would have $815.72. So again, she'd have to decide, is this good for her? Does she want to do this kind of an account? She's made a little, let's see, about $65, a little over $65. So maybe to her, that's pretty good. But in 7 years, $65 is not a lot of extra money. Okay, not everything increases. So the last few examples, the last few formulas we've been using, it is an increase in money. But a lot of things in life decrease in value. So when we have something that's going to decrease in value, we have to do some subtraction. So as we look at when a value decreases, I'm going to still use my capital A, that final amount, and then we have a capital P, but this time we're going to think about 1 minus R. So we're going to decrease for a certain amount of years. So in this case, we're just looking for something that's going to depreciate. So one of the most common things that depreciates is a car. So let's look at example 4. It says that Jeff has bought a new car for $27,500. And the car's value decreases 8% each year. So unfortunately, most cars you buy, your parents buy, when you drive them off of the lot, they decrease in value. And it's telling you it's going to decrease 8% every year. So again, we're going to be thinking 0.08 as we calculate. So we're wondering, how much will the car be worth in 15 years? So I'm going to think about using my decreasing formula up here. We know right now the initial amount of this car. Right now it's $27,500, but it's going to decrease. So that value of my car is going to decrease by 0.08 every single year. And we're looking for 15 years. If we own this car for 15 years. So into my calculator, I'm going to start with that 27,500. And I'll go ahead and use a parenthesis, 1 minus 0.08 for an exponent of 15 years. So according to this, if we bought a car after 15 years, it's going to be worth about $7,800. Whoops, I just realized I think I put too many zeros. Let me do this again really quick. Let's see, 27,500. And then in parentheses, 1 minus 0.08 to the 15. Oh yeah, that's better because my last one would have appreciated and it was supposed to depreciate. So $7,873. And let's see, 18 cents, because we would have an 8 that rounds that 7 up. So if we bought this car, or if Jeff bought this car, 15 years later, it would be worth just a little under $8,000, which that's a lot of money to lose over 8 years, especially when it starts with $27,500 or $27,500. But this does happen to a lot of cars. So example 5, kind of like your assignment, I'm not going to tell you specifically what equation that you need to use to help you calculate. You're going to have to really look for those keywords of how often the interest applies. Is it increasing? Is it decreasing? And notice it says to round answers to the nearest cent. So that's pretty much what we've been doing. So example A says that Emily invested $1,250, and after 2 years, she had $1,281.45. So kind of interesting. It told us that initial amount, but it's also given us the ending amount on this one. What it's asking for is what is the interest rate. So we're going to have to find that percent. Now it did increase. It went from 1250 to 1281.45. So I know that it's increasing. So if the interest rate was assessed, it says once a year. So once a year is kind of telling me that I have to use that original formula because that's when our interest was assessed once a year. So we want to use this original simple interest equation, as it's called, and I'm going to plug in what I know. Now this time I do know my ending amount. It's $1,281.45. I also know that initial value was $1,250. What I don't know is my rate. And it says that we did this for 2 years. She's invested this for 2 years. So now I have to work backwards a little bit. And this is one of the reasons that these problems are in secondary too, is because we know how to take care of a problem like this. So I know that I have to take a square root to get rid of this squared, but I can't take a square root of this expression because I right now have this 1,250. So let's divide 1,250 over to this 1281.45. So I'm going to use my calculator. 1281.45, I want to divide by 1250. Now I may get quite a few decimal places here, and this is not my final answer, so I probably would like to use all of them at this point. So I'm going to take, oops, I realized I forgot the one. Wait, I'm having a hard time. 1281.45 divided by 1250. So again, I just want to use all of those decimal places. So that would give me 1.02516, and that's equal to that 1 plus r squared. So now my square term has been isolated, so I can take the square root on both sides, and we know when we're solving an equation, when we take a square root, we're going to end up with a plus or minus. So I need to take the square root of that answer, 1.02516. So again, I know I'm going to get a really big decimal, and this is not my final answer. So it's okay if you don't write down all of the decimal places, but you probably want to give yourself several of these. I'm going to go ahead and write out all of them because I'm going to just keep track of all of this. So if I'm looking for my rate, I'm pretty close. All I need to do is subtract this one over to this other side. So I'm going to think about what I have. I have r now being equal to, I'd have to subtract that 1 over, but then I have plus or minus this decimal. Now remember, this is a rate that we're looking for is supposed to be increasing. It's been assessed 2 years, and we had a bigger amount than what we started with. So I want to make sure that I end up with a positive rate. I don't want to be decreasing. So as I think about this, if I take -1 and I add it to 1 point, I'm just going to go ahead and type in all those decimals. I could go and copy that if I wanted to. That's going to give me that positive value, where if I press subtract, I would have -1 minus 2 point, all of that. I'd end up with a -2 point something. And I don't need a negative rate. I need a positive rate. So I'm not going to use my other version of this. I'm going to keep what I've got here. So I probably, again, don't need all of these decimal places. When I'm looking for a rate, usually 2 decimal places is good. So I know that when I move my decimal 2, I'm going to end up with 1.25. And I want this to be written as a percent. We calculate with decimals, but we're going to write these as percents. So be thinking about it when you're solving. If it's increasing, we definitely want a positive rate, not a negative rate. All right, let's look at B. Sam invested some money in a CD with an interest rate of, so again, I'm thinking move that decimal place 2 places. And it was compounded quarterly, so not every year. So I'm already thinking, what equation do I need to use? And the one on that front side was called compounded interest. And it says if I take my amount this time and I'm going to have to divide that rate by a certain amount of times. In this case, it was quarterly. So quarterly, there's 4 quarters in $1, so there's 4 quarters in a year. So my end value is going to be 4. So we're looking for how much money did Sam invest if he had $1,500 after 10 years. So again, a little bit different kind of a question. We already know how much he had at the end. He had $1,500 after a 10-year period. So when I go to plug this in, my $1,500 is my A. What I don't know is my P. How much money did he actually invest? So let's plug in what we do know. We know the rate, and I've already moved my decimal. And we're doing this 4 times a year. So we're dividing by 4, but we're doing this for 10 years, or it's been happened for 10 years. So 4 times 10, this is happening 40 times. This interest has been happening. So in order to solve this, I need to isolate my P, which means I need to divide by all of this. So I'm going to take 1,500 and my P, I'll keep those the same. And I need to figure out what this 1 plus this fraction to the 40th power is. So I'm going to go ahead and put parentheses and do 1 plus and put in that fraction, 0.0115, and we're dividing that quarterly, so by 4. And we're going to do this for 40 total payments here, 4 times 10 years. So I'm not shocked that I have this big decimal. I'm going to go ahead and write out the whole thing. This is not my final answer, so I'd like to use all of this. But I need to do 1,500 divided by this now because I'm solving for P. So 1,500 divided by that decimal. I'm just going to use all of those values. And this will tell me what we started with, what was the principal. So for this particular problem, and again, we're going to round a little bit with money. That 9 rounds the 6 up. So it looks like we started with about $1,337.27. So Sam started with about that much money, and after 10 years in the CD had $1,500. So your assignment, you're going to have to decide which of the formulas that you're going to use to help you calculate, and make sure that you're reading the question correctly. What is it that you're looking for? Are you looking for the final amount, the principal amount, the interest rate? Make sure that you're solving that accordingly. So go ahead and self-assess, and good luck on your assignment.